Hello and welcome. My name is Dr. Mark Taylor. This is Delaware Tech Physics 111 Lesson 6. This is part of the third lesson of Unit 2 on forces and energy, and it's a continuation on the section on forces, Part 3, which also includes work and power. In this lesson, we're going to first review Newton's three laws of motion. First law, the law of inertia. The second law, the law of acceleration. And the third law, the law of action and reaction. We'll go through a practice quiz with a little over 30 questions. Most of these will be pretty straightforward. We have some advanced topics that you are not directly responsible for. Forces at an angle, which we've done to a certain extent in the last lesson. Newton's law of universal gravitation. This is the full formula for the gravitational force, which you haven't seen before. We've been using the approximation formula of the weight equals m times g, but this is a more elaborate formula. We'll briefly mention centripetal acceleration and centripetal force. Now, you may have heard the term centrifugal with an F in the middle of the word. Centrifugal force. This is actually the true force. Centripetal force is the true force. Centrifugal force is something that's an apparent force, and we'll talk about what that means. Then we'll discuss the physics concept of work. This is not necessarily the way you think of work in everyday English. There is a very specific definition of work in physics, and it has a certain calculation, but we're going to use a simplified form of that calculation for most of our calculating of work energy. All right. The unit of energy is the joule. We'll talk about the joule. And then we'll talk about a concept called ideal mechanical advantage. This is a number it's another unitless number that tells you how useful a machine is in terms of making your life a little easier, in terms of telling you how much less force you have to use to get a job done, and letting the machine do the big force for you. Then we'll talk about the efficiency of machines. Machines aren't perfect, so there's a real-world percentage for any machine. Then we'll talk about the concept of power. Power and energy are not the same thing. Power and work are not the same thing. Power is a term that means the amount of work per time or the amount of energy per time. And then we'll close this lesson with a number of example practice problems on work and power. All right, let's start by reviewing Newton's three laws of motion. Newton's first law of motion, the law of inertia. So inertia is the resistance to changes in motion, and it's really another way to think of mass. The more mass an object has, the more force is necessary to change that object's motion. The more force is necessary to accelerate that object. And acceleration really just means a change in velocity or a change in movement. So Newton's first law says an object at rest tends to remain at rest, and an object in constant motion, that means constant velocity or constant speed along a straight line path, will remain in constant motion unless acted upon by an external net force. All this means is if it's stopped, it's going to stay stopped. If it's moving, it's going to keep moving the way it was moving unless there is a net force on that object. And contrary-wise, if there's no net force on the object, in other words, if net force is zero, if the sum of all the forces on the object adds up to zero, or there are no forces on the object, if that's zero, then there is no acceleration either. Acceleration is zero. If acceleration is zero, that means there's no change in velocity. The delta V is zero, and that means that the velocity is constant. It is very important to remember, it does not mean the velocity is zero. It means it's constant. It could be constantly zero, or it could be constantly some other value, positive, negative, or at some angle. All right. And this is part of the 5 things all or nothing test that we mentioned in a previous lesson. All right. So Newton's second law of motion, this is also called the law of acceleration. I'll scroll this up a little bit. This is a law that relates the net force on an object, the mass of the object, and how much that object will accelerate. So when a net force acts on an object, the object will accelerate. Now, how much it accelerates is described by the formulas below. These two formulas, net force equals mass times acceleration, or acceleration equals net force divided by mass, these are the exact same formula, just rearranged in two different ways to make it easier to see the relationships between these three different variables. All right, so acceleration A is proportional to the net force on an object. In other words, if we increase the net force by a certain factor, let's say we increase the force tenfold, the acceleration will also increase tenfold. If we cut the net force in half, the acceleration will also be cut in half. Whatever we multiply or divide by one, we will multiply or divide by another. Okay, and that is assuming that the mass is constant. So we see that in these equations. If you look at them, you'll notice that if you keep m constant, whatever you do to A is going to happen to the force net. All right, so this is actually the reason why we follow through in sports. If you're not familiar with that term, follow through means when you're using a baseball bat on a ball, or a golf club on a golf ball, or even your hands on a basketball. The more you are contacting the object, the more time there is for you to put a force on the object, and the more you will end up accelerating that object, making it go faster and faster. The second that ball is released from the bat or the golf ball of the golf club or your hands, the moment it is released, the force has stopped on the object, and the ball will continue moving with the last velocity it had as it's being released from your hands or the club or the bat, etc. All right. Newton's third law of motion. This is called the law of action and reaction. And this says that whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first. And this is a law that you may have heard described as, for every action there's an equal and opposite reaction. Now, what you have to understand about Newton's third law is these two forces do not fight each other. They don't stop the motion of an object, because the first force is acting on one object, the second object, and the second force mentioned here is acting on the first object. And if you're interested in how an object moves, you only care about the forces on that object, never by that object. So these two forces cannot cancel each other out. They're acting on different objects. Now, these two forces can be called the action force and the reaction force, but it really doesn't matter which one you call the action and which one you call the reaction. You can call the first one the action, the second one the reaction, or the other way around, no matter how weird that may seem if you're talking about real-world objects. If I'm pushing a wall with a certain force, the wall is pushing back on me with exactly the same force in the opposite direction, and you could call either one of those the action force, though it seems odd to call the wall pushing you as the action. You tend to think of that as reaction, but the fact is these two forces happen at exactly the same moment in time. There is no one force causing the other force to happen. They happen simultaneously. So let's look at some practice problems involving the three laws of motion. And many of these problems will be giving you a situation, and then you're asked to pick, does this relate to the first, the second, or the third law? All right, so question number 1 says, the law that describes action-reaction pairs. Well, that law is Newton's third law of motion. That is the action and reaction forces are exactly equal in strength, but in opposite directions. The object A will act on object B and by a force, and then object B will impart the same force on object A, exactly the same force at exactly the same moment in time. They just happen to be forces in the opposite directions to each other. All right. Question number 2, the law that describes F equals ma. Well, this is really the net force equals mass times acceleration. And this formula is the description of Newton's second law. It relates the net force to the mass and the acceleration of that mass. If you have a certain net force on a certain mass, it will cause that mass to accelerate with an acceleration equal to a. And you can rewrite that formula as the acceleration equals the net force on the object divided by the mass. So you'll have to determine the net force on the object and divide that by the mass to get its acceleration. Or if you're given the acceleration, you can multiply the mass by the mass and get the net force on the object. All right. Okay, looking at number 3, the law that describes inertia. Well, inertia is the resistance to changes in motion. What is changes in motion? Changes in motion means changes in velocity. So inertia means it's a resisting changes in velocity. Changes in velocity is another way to say acceleration. So inertia resists acceleration. So Newton's first law, the law of inertia, literally tells us that an object has inertia, and that's usually because the object has mass, and the more mass it has, the more inertia it has. And if the object is stopped, it's going to stay stopped. If the object is already moving, it's going to keep moving the way it was moving, unless an external net force acts on that object, and then you can change the speed or the direction of the object's movement. Okay. Which law is associated with a box at rest on the floor? So we have the floor, we have a box, and it's just sitting there. I'll just make our box here, and it's just sitting here. The velocity of this box is 0. The acceleration on this box is 0. And the net force on this box is also 0. It has a weight force. I'll write it over here. The weight force is pointing down, and the floor is pushing on the box back up. So there are 2 forces on the box. One from the earth pulling it down, that's the force of gravity, also known as weight, and one, the floor pushing back up, keeping the box in place. So the box isn't going anywhere because the net force on the box is 0, and it's going to remain at rest. So it's at rest, it will remain at rest, and that's Newton's first law. Now you might say, well, wait a minute, Newton's second law might be involved as well, and it sort of is indirectly, and that is because if you want to know how much force you need to accelerate the box by a certain amount, you would take the mass of the box and say, ask yourself, how much do I want to accelerate it? You multiply those 2, and that tells you how much net force you have to put on the box to make it change its motion. Right, let's take a look at the next problems. Number 5, you hit the brakes while driving your car. The physics book on your passenger seat suddenly flies forward and off the seat. Which law is associated with this? Well, what's the situation? You have a car, and I'll just draw the seat in the car. I'll just make a box that represents the car itself, and you've got a book sitting on the seat. Okay, there's your book in red, and it's sitting on the seat. The car and the seat are attached to one another, and everything is moving with a certain velocity v, and we'll make it go in the positive direction here. Doesn't really matter whether it's positive or negative. The car is going to the right here. And the seat is going to the right because it's attached to the car, and the book is sitting on the seat, and the book is also going with the same velocity. When you hit the brakes, that means there's suddenly a slowing down of the velocity, and that means there's a negative acceleration in the opposite direction of the velocity. The seat is part of the car. It is directly attached to the car. So when the car slows down, the seat slows down instantly. They're all one thing. But the book is not attached. The book continues to move with the velocity it always had and will fly forward. Well, Newton's first law tells us if an object has motion, if it's already moving in a straight line, and it's moving in a straight line, and it has a certain speed and direction, it has a certain velocity, it will keep having that speed and direction, that same velocity, that same motion, until a force acts on it, a net force acts on it. But at the moment the brakes are hit, the only force acting on that book is a little bit of friction holding it in place, and now the book will just go flying as the car is slowing down, because the book was always moving with this speed forward. It's the car that changed its velocity, going slower and slower. So this is an example of Newton's first law. The book has a certain amount of inertia, so it'll keep doing what it was doing. Now, eventually, the book will fall onto the floor of the car, be caught up by the car, and will slow down with the car. But at that moment, the book has the same speed as it always had, and the book will just fly forward. And the same thing happens if you're not wearing your seatbelt. This is why you wear your seatbelt, because when you hit the brake, you want to be part of the car. You want to slow down with the car at the same time. You don't want to go flying through the windshield. All right. Number 6, if you push harder with your leg muscles, you run faster, meaning you accelerate more. Which law is associated with this? Okay, well, this is a situation where pushing harder literally means you're increasing the net force that you're using on your legs, which will be pushing on the ground. That net force goes up. Well, it's saying the acceleration goes up. Well, that is a direct consequence of Newton's second law. The acceleration will go up if the net force goes up. You increase one of these, the other will increase. You can imagine if we say the mass is 100 kilograms, or we don't even need to use units. Let's say the acceleration is 1. Well, we're going to get a net force of 100. But if we increase our acceleration by 3, and we multiply that by 100, now we're going to get 300. So if I triple my acceleration, I'm going to triple my net force. If I triple my net force, I'm going to triple my acceleration. This is Newton's second law. Some of this here, so we have a little more room. All right. Number 7 says, I pull downward on a rope. The rope pulls upward on me. Which law is associated with this? Well, you have a force where you pull on a rope, and as a result, the rope pulls you. Well, this is Newton's third law. For every action, you get an equal and opposite reaction. And if we want to be careful about the signs, we say one is the negative of the other because they're in opposite directions to one another. Whenever you have Newton's third law, if something acts on something else and you want to know what the other interaction force is, all you have to do is switch the two objects and switch the direction, but the amount of force is exactly the same. So it's you pull on rope, the rope pulls on you. You're pulling downward, the rope pulls upward, the opposite direction. So this is Newton's third law. Number 8, I use the same amount of force to try to move a baby and to try to move a sumo wrestler. Now, those of you who may not be familiar with sumo wrestlers, this is a very famous Japanese sport. It's their national sport, and sumo wrestlers tend to be very, very large individuals. They tend to be in the ballpark of over 400 pounds very frequently. So much more mass than a baby has. All right. The baby accelerates more. All right. So you have a situation where the amount of force is the same. Well, let's look at Newton's second law again. The amount of force is the same. So we're going to keep this constant. 2 examples ago, we had the person, and we increased the force on their legs to make them accelerate more. So the mass of the person stayed the same. Now we're going to keep the force that the person is using on something else constant, but the mass is going to be different. We have 2 masses, a baby versus a sumo. And a sumo has much more mass than a baby does. Well, we can also rewrite this formula as acceleration equals net force over mass. If I'm dividing by a little number, if the mass of the baby is tiny, and I divide a certain amount of force by that, I'm going to get a big acceleration. But if I divide the same force by a giant mass, I'm going to get a small acceleration. So this is a direct consequence of Newton's second law. Okay, number 9. Type of force that arises from touching, such as an applied force like push or pull. All right, so this is asking what category of force would an applied force like a push or pull fall into? Do we call that a Newton force? Do we call that a field force? Do we call this a contact force or reaction force? Well, this is actually something we have not directly talked about. We have 2 major categories of forces: contact forces and field forces. Contact forces are forces that one object puts on another object only while they're touching each other. So a push, a pull, those are contact forces. Friction is a contact force, all right? The normal force, pushing back up on a book sitting on a table, or you standing on the ground, that's a contact force. Field forces are something we have definitely not discussed in this class, and these are due to fields this is a term physicists use to describe forces that act, quote, at a distance, forces that don't require contact between them. So electrical force, you could have a positive charge here and a negative charge here, and they'll attract each other, but they don't have to be touching to attract each other. You could have a north pole of a magnet and the north pole of another magnet will repel each other, and they don't have to be touching for that force to happen. These are referred to as field forces. Gravitational force is another field force. If I have the Earth, yes, I can be touching the Earth, but the fact is, I could be an astronaut out in space and feel the Earth's pull as well. I don't have to be contacting the Earth itself to feel the gravitational force. So gravitational force, electric force, and magnetic force are all examples of field forces. Number 10, the type of force that can act without touching, such as magnetic or gravitational force. Well, we just answered that question. That's a field force. So gravitational force, magnetic force, electric force, these are all field forces. Number 11, a force that prevents motion due to surfaces rubbing surfaces. Okay, if I've got a floor and I've got a box on the floor and I'm trying to move that box, there's going to be a force fighting me. Well, that force is the frictional force. The force, number 12, the force along a taut rope or wire or rope. Any long, thin object, if it's pulled tight, if it's pulled taut, there is a force along that object. You can imagine if two people are playing tug of war with each other and they're fighting, and pardon my horrible drawing, but they're pulling on this rope. There are forces all along that rope in both directions. And the force in one direction is exactly equal to the force in the other direction, and it's the same force everywhere along the rope. Everywhere I look, it's the exact same force, and it's in both directions everywhere I look. These are supposed to be arrows along here. This is called the tension force. Sometimes it's abbreviated as capital T in a lot of textbooks. We're going to abbreviate all the forces with force sub some letter. So it's F sub T for tension. Number 13, the force of attraction between any masses. Well, this is the gravitational force. Your weight is the attraction between your mass and the Earth's mass. The center of the Earth's mass and the center of your mass. There is a force between any two masses. And in this case, the Earth's mass is much, much bigger than yours. But the fact is, there is a force that the Earth is pulling on you. And believe it or not, at the same time, you are pulling on the Earth with exactly the same force. That's actually Newton's third law. It seems odd, but if you have a certain mass and it works out that your weight is, say, 600 newtons, that means the Earth is pulling on you with a force of 600 newtons. It also means that you are pulling on the Earth with a force of 600 newtons straight up. So this is gravitational force. And you'll see in the actual formula for gravitational force, both masses are important. You might say, well, wait, I've always done weight by just taking my mass and multiplying it by little g. Well, yes, your mass is one of the two masses. The little g we don't tell you is actually composed of a bunch of numbers, and one of those is the mass of the Earth. So they're all multiplied and divided by each other in a certain formula to give us this little g. But the little g is actually more complicated than you might think. But it includes the mass of the Earth in that number. All right, number 14, a force that prevents penetration through a surface and acts perpendicularly to the surface in contact. Okay, so you have a box sitting on the floor. We know that the Earth is pulling on that box with a force of gravity we call weight, but at the same time, the floor or the ground or the table is pushing back up, straight up, at an angle that's perpendicular to the surface. And in fact, if we had a surface at an angle and we put that box at an angle, gravity would still be pulling straight down because it's to the center of the Earth, but the normal force is always perpendicular to the surface, even if the surface is tilted. If I tilt it even more, the normal force is tilted even more. So the normal force is always perpendicular to the surface, and it's what keeps the box from going through the table. It's what keeps us from going through the floor or the ground outside. Number 15, which is not an example of an action-reaction pair. All right, you're looking for A acts on B in a direction, and then B acts on A in the opposite direction. All right, so part A says, I push on the wall to the right. The second part of it says the wall pushes on me to the left. Well, I and wall are switched, and the direction is switched. Oh, so now it's wall pushes on me to the left. That one works. Okay. B, the oar pushes backwards on the water. Well, we switch the two objects. The water pushes on the oar, and the direction is forward. Well, that one checks too. Now we look at the last example. I'll do this in a different color. The hammer pushes downward on the nail. Well, the other sentence says the wood pushes upward on the nail. Well, they have to be the same two objects. If it's hammer pushes on the nail, then this has to be the nail pushes on the hammer. The only way to make a Newton's third law interaction pair, that's what the reaction and action and reaction are called. They're called an interaction pair. You have to take the exact same objects and switch which one's doing the force on the other, not just change the direction of the two like they did. So C is the correct answer for this problem. Number 16, what is the mass of a 980 Newton object? Well, Newtons is a measure of force. Weight is a type of force. That's F sub G. We know this equals M times G. We are told that the force is 980 Newtons. We're not going to worry about plus and minus signs right now. We could put it in there. We could just remind ourselves with little parentheses. We are looking for the mass, and gravity is 9.8 meters per second squared. And we can remind ourselves that's a negative also. So we're just going to divide 980 by 9.8. And the answer will be in units for mass. Well, the mass unit is kilograms. So our answer is 100. 980 newtons divided by 9.8 meters per second squared equals 100 kilograms. So just keep track that if you're calculating a mass, it should be in kilograms. Number 17. The mass, if the mass of an object is 10 kilograms, what's its weight? So we're using the exact same formula. The weight, gravitational force, equals M times G. We know what M is. It's 10 kilograms. We know what G is. It's 9.8 meters per second squared. Yes, technically it's negative. We're not going to worry about the negative for now. We multiply these together. We get 98, and the unit for weight is newtons. And if you want to remind yourself, it's in the downward direction, negative, but it's just asking for the weight. So it's 98 newtons for number 17. Okay, number 18. A 20 kilogram object sits on a horizontal table. What is the normal force pushing upward from the floor? Well, remember I told you anytime you get a mass, calculate the weight right away. Anytime you get a weight, calculate the mass right away. This will usually be a useful second value to have in a lot of these problems. And this is just another example of that. So we have this horizontal floor, and we have some object, and it has a mass of 20 kilograms, 20 kilogram mass. If it has mass, it's going to have weight, at least if it's on the earth. It's going to have weight, and there's going to be a normal force in the opposite direction. If there are no other forces acting on the object and it's a horizontal floor, the size of the normal force will be exactly the same as the size of the gravitational force, the weight force. They're just opposite directions. And we're not going to worry about directions. It's just asking for how big it is right now. So we need to know what the weight force is. M times G is the weight force. That's 20 kilograms times 9.8 meters per second squared. And that works out to 196 newtons in the downward direction, which means our normal force is 196 newtons in the upward direction. Put the little plus sign there. Okay. Number 19. If a 98 Newton object, okay, they're telling you the weight right away, get used to calculating the mass. A A 98 Newton object. Newtons are going to be a unit of force. Weight is one type of force, but if it says a certain number of Newton object, it's talking about the weight of that object. So if you get the weight, calculate the mass. If you get the mass, calculate the weight. What is the normal force pushing upward from the table? Okay, well now you've got this object sitting on a level table, and we know its weight force is 98 newtons, and we know that's in the downward direction. We'll just remind ourselves a negative sign, but we don't need to know that. Well, there's going to be a normal force from the table pushing back up, keeping that object from going through the table. That has to balance it. Well, if it's 98 newtons down on the object, and the object is not floating up into the sky, and it's not crashing through the table towards the center of the earth, we know the normal force must match, because the net force, vertical net force on this object is 0, so they have to balance each other. They must be the same value. So it's 98 newtons is the normal force, and of course that's in the positive direction. Now for number 20 and 21, I'm going to display both of these at the same time because the beginning of each of these questions is exactly the same. You push a 100 kilogram crate to the right, okay, the 100 kilograms is the mass, and you push it with a force of 500 newtons, and the crate moves with a constant velocity. Okay, that's common to both of these questions. It's a 100 kilogram mass, it's moving to the right with a constant velocity, and it's due to a push force of 500 newtons to the right. All right, so let's draw this diagram out a little bit. We've got some object here, crate, it's on the ground. We know its mass is 100 kilograms. There is a weight force as a result of its mass and gravity. That's equal to m times g. That's going to be in the negative direction. We know that there is a force up from the ground, keeping the crate from going through the surface of the ground. That is the normal force. It is pointing up, so I'm going to give it a positive force, and it's going to be the same magnitude as the weight force because those are the only vertical forces. We also have an applied force to the right of 500 newtons, and we know this object is moving at a constant velocity, and the constant velocity is in both of these problems. Well, the second you see constant velocity, bells should be ringing in your head. You should immediately think, okay, the velocity is constant. What do I know from that? Well, it doesn't matter whether it's constantly 0 or constantly something. If it's constant, that means the velocity is not changing. That is, the change in velocity is 0. If the velocity is not changing, then there can't be any acceleration. So the acceleration is 0. If there's no acceleration horizontally or vertically, it means there's no net force horizontally or vertically, but we're interested in the horizontal right now. So I'm just going to say the net force horizontally is 0. Because it's not floating up into the sky or accelerating towards the center of the earth, we also know its vertical net force is also 0 because that acceleration is also 0. So we know a lot of information just from the question. All right. So the first question, 20, says, what is the net force in the horizontal direction? Well, we just established if it's moving at a constant velocity to the right, that means there's no net force in the horizontal direction. Therefore, the net force is 0. There is no option for 0. We've got 100 newtons, 500 newtons, 980 newtons, or none of the above. Well, the none of the above is 0 newtons, and that's our answer. It's no net force, 0 net force. Question 21 asks, to continue this thought, what is the magnitude of the frictional force on the crate? Well, we never mention a frictional force on the crate. but we know the velocity is constant. So I'll use a K for constant here. If it's constant, we know the net force in the horizontal direction is 0. Well, we only know about one force in the horizontal direction. That's the applied force, the push force. Well, if it's being pushed with 500 newtons and yet there is no net force, there must be a balancing force in the exact opposite direction, also 500 newtons, but pointing in the negative direction, and that is our frictional force. So we now know the frictional force must be equal to 500 newtons in the negative direction. Number 22, a book is at rest on a table. Okay, it's at rest on a table. The book remains there because A, there are no forces acting on the book. B, it moves, but the movement is too small to be seen. C, there is a net force on the book, but the book has too much inertia. Or D, there is no net force on the book. Well, let's diagram it out. We've got a table, and we've got a book sitting on the table. Well, we know the book has mass, and therefore we know there is gravity affecting it, and therefore the book has weight. And we know the book is not breaking through the table and heading towards the center of the earth. So that weight force must be equally balanced by a vertical normal force of the same magnitude, same size. Are there any other forces on the book? Well, it's not moving to the right. There might be an applied force to the right, and there might be a frictional force to the left, but there's no mention of it. It's just sitting there at rest on the table. These are probably our only two forces on it, and they balance each other out. So it's not that there are no forces, because we know there's at least a weight force, and if there's a weight force, there's probably a normal force to balance it. So that can't be right. It moves, but the movement's too small to be seen. Well, there's no mention of movement. It says at rest. At rest means no movement, so that's out. There is a net force on the book. Well, the net force on the book vertically, since there is nothing horizontal in here, is just the sum of the normal force in the positive direction, up, and gravitational force in the negative direction, that is down, but that's equal to 0. So you could, if you want to be really pedantic about it, you could say, yes, there is a net force, it just happens to be equal to 0. But that means there's no net force. But it says because the book has too much inertia. Well, too much inertia is pretty similar to saying too much mass. Well, it's not because the book has too much mass. If the book was a small book, it would still remain at rest if there was no external force on it. So it's not that it's too small a book. You could have a tiny flake there, or a penny, or a speck of dust. It's going to sit there unless there's a force on it. So we know that the sum of the forces equals 0, and therefore there's no net force on the book. So D is our correct answer. Now, there's a little follow-up here. There are forces acting on the book. Yes, we know that. And they are only in the y direction. That's the gravitational force, F sub g, and the normal force. Okay, the force of gravity, otherwise known as weight, is downward, and the table exerts an upward normal force. Well, we already discussed that. And because the vertical net force is 0, we know that because the vertical acceleration is 0, it's not changing, then those two forces must balance each other out. All right, number 23. A puck slides on the ice at a constant velocity. Okay, immediately you see constant velocity. Tells you lots of information. Velocity is constant. It doesn't mean 0. It just means it's not changing. If the velocity is constant, The change in velocity is 0. The acceleration is 0. The net force is 0. Now you notice 3 of these things say 0. This one just says constant. It could be 0 or it could be just any other number that's not changing. So don't make the mistake of saying the velocity has to be 0. If it's at rest, it's 0, but if it could be moving along at a constant velocity, which is what it says. It says slides at a constant velocity. What's the net force acting on the puck? Well, we know the net force is 0 because the acceleration is 0. The acceleration is 0 because there's no change in velocity. All right, so the puck is moving on the ice at a constant velocity, therefore it's not accelerating. That's our big clue. If it's not accelerating, there is no net force. There's no getting around that. Little question, what are all the forces currently acting on the puck? Well, if the puck is just sitting on the ice and it's sliding, and we have no reason to believe that there's any push force on this, and we're going to assume that a puck on ice has almost 0 friction, we don't need to have any horizontal forces. But of course, we know the puck has weight, and we know the puck is supported by the ice. So there is an upward support force that we call the normal force, and there is a downward weight force. That is the gravitational force. Number 24, a smooth, flat stone is sitting on a frozen pond. So it's a stone on ice. You kick the stone, it slides, slows down, and eventually stops. What do you conclude? Select all correct answers. So there could be as few as 0 correct answers or as many as 4 correct answers. Let's look at them one at a time. A, the pushing force stopped. Well, we specifically state that you kick the stone. Well, you're not kicking it and pushing it with your foot forever, so clearly the pushing force did stop. That one's easy. B, no net force acted. Well, if no net force acted, then the next logical conclusion is that there was no acceleration, which would mean that there's no change in velocity. But the problem is, it says it slowed down. In fact, it says it slid first, which is speeding up, then it slows down. So this is not true, and this is not true. Therefore, this can't possibly be true. So that's incorrect. C, a net force did act. Well, we just established if there is a change in velocity, it went from sitting on the frozen pond to sliding, and then it went from sliding to slowing down. That's actually 2 changes in motion, 2 changes in velocity, 2 different accelerations. The first one was from the kick. The second one, slowing down, was probably from the friction between the stone and the ice. Yeah, there's not much friction, but there's enough to eventually slow the stone down. So yes, there was a net force acting on it. That net force may have changed. The kick presented one net force, and then the friction changed that net force, and eventually the stone came to a stop. But there definitely was a net force acting on it, or we wouldn't see any change in motion. D, the stone has a natural tendency to be at rest. Well, this is actually something that is clearly not true, but believe it or not, 2,400 years ago, back in the time of Aristotle in ancient Greece, that's what he believed, and that's what he taught, and that's what people believed for a long, long time. In fact, it wasn't until possibly the 1500s that people started thinking, well, this doesn't really make sense, and people like Galileo and eventually Newton changed how we think about the natural laws of motion and forces in the world. So there is no natural tendency for anything to be at rest. If there are no individual forces on the object or no net force on the object will stay doing whatever it was doing. That's Newton's first law. If it's at rest, it'll remain at rest. If it was already moving, it'll keep moving, but it's not going to change how it moves. It's not going to speed up or slow down or change direction unless there's a net force on it. So this is also not true. And our follow-up here says after the stone was kicked, that's an applied force. no force was pushing it along anymore. Once your foot leaves the stone, that applied force is no longer happening. However, there must be some other force acting on it to slow it down, and that's most likely friction. The extra question here is, what would you do to keep the stone moving? Well, you'd have to keep applying a force. Either keep pushing it or kick it over and over again, or have one long kick, which is not a realistic thing to do. Okay. Number 25. What can you say about the force of gravity? Remember, this is the weight acting on a stone versus acting on a feather. The tube is evacuated, if you look at this picture here, so there is no air inside. Evacuated means you've created a vacuum on the inside by sucking all the air out of the tube. You can do that with a pump. All right, so is the force of gravity, that is the weight, greater on the feather? Is it greater on the stone? It's the same on both, or they're both zero when they're inside a vacuum of the evacuated tube. Well, I'll tell you right now, having no air does not change the fact that the force of gravity from the earth is acting on the feather and the stone. The earth will still have gravity on these objects, whether there's air or not. So the last answer is definitely not correct, so we can remove that one. All right, so is the weight greater on the feather, weight greater on the stone, or is it the same? Well, it's not the same. We have to remember, how do we calculate weight? Weight is equal to, remember, weight is force of gravity, equals mass times gravity. Well, G is not going to change for a feather or for a stone. It's the same G because the earth is the same earth with the same gravity on gravitational force on these objects. All right. What is changing is the mass. If we increase the mass, we will increase the force, specifically the weight force. So the weight is greater on the stone, just like if you were to hold a stone and a feather, the weight of the stone is greater than the feather. There is no trick here. Okay. Follow up. The force of gravity depends on the mass. That's what we just said. The stone has more mass, therefore more weight. But that's only true, by the way, if there's gravity. If you were out in deep space, a feather and a stone don't have weight at all because there's nearly no gravity when you're out in deep space. All right. They have different mass and therefore different inertia, but they don't have any weight out in deep space. You have to have gravity for that. The fact the tube is evacuated of all air makes no difference. All right. So let's look at number 26. Again, we have an evacuated tube. There's no air inside, and the question says, what can you say about the acceleration due to gravity, that's little g, acting on the stone versus acting on the feather? Well, it doesn't matter whether it's a stone or a feather. The g, the acceleration just due to gravity. In other words, if the force of gravity was the only force on the object, every object would have the same acceleration downward towards the earth. That acceleration would be g, negative 9.8 meters per second squared, or simply 9.8 meters per second squared in a downward direction. They do not change. Now you may say, well, wait a minute, if I have a feather and a stone and I drop them in outside of this tube, the feather floats much slower than the stone does. Well, that's because there's another force acting on both of them, and that is air resistance. But the air resistance on a stone is so tiny, especially compared to the weight force, that it's really not important. So if we were to draw this out, we would say the object has a weight force, and that weight's going to be different for the stone versus the feather. But there's also another force called the force of air resistance, and we can abbreviate that with an F sub R. It could be a lowercase or uppercase. The force of air resistance is also known as drag. We also use that term. And the drag on a stone is almost nothing, so we don't worry about it. The stone has to fall for a very long time and get faster and faster and really have a lot of friction with the air before it becomes important. But a feather, the instant you drop a feather, the air resistance builds up immediately because the feather has lots of surface area, it catches lots of air, it has lots of friction with the air, and therefore lots of air resistance force pushing it up as the gravity is pulling it down. So in that case, they don't have the same acceleration. But in a vacuum tube where there's no air, this disappears, and the only force on either one of them is the weight force, and therefore the only acceleration on both of them is g, and we call that situation free fall. If an object is falling only due to the acceleration because of gravity, we call that situation free fall. Once you throw in air resistance, once air resistance becomes significant, it's no longer free fall. You can't use that term. We tend to use the term non-free fall in the case of a feather floating in air. But these are in an evacuated tube. There is no air, so they both have exactly the same acceleration downward g. And if you ever watch a video of people dropping stones or chunks of metal and feathers inside a vacuum chamber or a vacuum tube, it's kind of shocking to watch a feather fall down very quickly to the ground as fast as a stone or a rock or a chunk of metal drops down to the ground, getting faster and faster as it falls. So the acceleration is given by the formula of net force divided by mass. Now, yes, they have different masses, but they also have different net forces. And the net force, in this case, when there's no air, the net force is the same as the weight force. So that ratio is the same as the weight force divided by the mass. But we know that the weight force divided by mass is simply g. So that means the acceleration we observe for any object in a vacuum is g. And that's represented by this formula right here. So if both objects have an acceleration of g, when there's no air resistance, then you'll see them both fall. They'll accelerate as they drop and hit the bottom of the tube very quickly. So without any air resistance, we call that free fall. If the air was present, we would have a totally different situation. The air resistance on the feather would grow extremely quickly and match the weight force of the feather immediately, and you'd have a situation where the weight force is pointing down and the feather's air resistance would match in size the weight force almost immediately, and these two forces would cancel and there'd be no net force, and the feather would float down at a constant speed, not like when you drop a rock. Okay. Number 27. A block of mass m, okay, so you're told the mass is m. It rests on the floor of an elevator that is moving upward at a constant speed. What is the relationship between the normal force, in other words, this is the force from the bottom of the elevator, we'll call it a room that's moving up. The floor of the elevator will push up against the object inside the elevator as the weight is pushing down. Well, when that happens, if the whole elevator is going up with a constant velocity, that means the acceleration is zero. And that means the net force in the vertical direction is also zero. Well, if the net force is zero, then you have the object's weight force pointing down, and you have the normal force from the surface of the elevator pushing up on that object. Those two forces are going to balance, and in that case, they'll be exactly equal. And that is true whether the elevator is dead stopped, because that's a constant velocity, constantly zero, or it's constantly moving up at a constant speed or moving down at a constant speed. It doesn't matter whether the elevator is dead stopped or moving up or down at a constant speed. then the net force is 0, and therefore these two forces, the normal force and the weight force, will be identical in size. They'll be in opposite directions. So that's the takeaway. Whether it's at rest or at constant speed, they'll be the same. There's no acceleration in the case. This is different from when an elevator just starts to move, because it's going from no velocity to something. If it's moving up, it's an acceleration upward. If you started at the top of a building and you suddenly start moving down, for that brief moment, it's going to be going downward and accelerating downward, because it's going from nothing to something downward. Those are accelerations, and now the forces are not equal to each other. But if the velocity is constant, meaning 0 or just constant up or constant down, then the two forces are identical to one another. Now, here we have a different situation. The block of mass m rests on the floor of the elevator. That's true. But now the elevator is accelerating upward. Okay, so here's the so-called room of the elevator, the box of the elevator. And you are told the whole thing has an upward acceleration. Well, that means there's an upward net force. There has to be an upward net force. The direction of the acceleration and the direction of the net force are always identical. So what this means is, you know that the two forces, the weight force and the normal force, are not balanced. And in fact, there's an imbalance between them, with a net total that is pointing upwards, which means if you have a weight force that will represent with this arrow pointing down, there must be a bigger normal force pointing up that more than compensates for the weight force, enough to give it an extra net. Because the net force, remember the net force, and I'll write it up here, the net force in the vertical direction is equal to the normal force pointing up plus the weight force pointing down. Well, this can't be 0 anymore. It's now a positive number, because the acceleration is a positive number, meaning it's pointing upward. So we know that the net force must be bigger than the gravitational force in this case. And in fact, if you are in an elevator, let's say you're starting at the bottom of an elevator and it's not moving, you hit that button, you're going to feel the elevator move up into you. And for that brief moment, you're going to feel heavier than when you're just sitting still in the elevator. And the reason is, your perception of weight is actually not due to the weight force, it's actually due to the normal force. When you step on a scale and the scale reads some value, the number on that scale represents not your force down on the scale. It's actually the scale pushing back up against you. So what you read on a scale, a weight scale, is actually the normal force pushing up. So if you were standing on a scale in the elevator, for that brief moment when you hit the button and it just starts to go, the weight that appears on the scale that you're standing on in the elevator will actually be heavier than you really are. Let's say you weighed 130 pounds. For a brief moment, the elevator moves up into you, and that force of moving up into you will increase your, quote, apparent weight, which is really the normal force. And the scale might read 140 pounds or 150 pounds, depending on how much the elevator accelerates upwards. All right. So the block or the person or whatever is inside is accelerating upward, and must have an upward net force on that object in the elevator. And the only way to get that is for the normal force to be more than equal to the weight force. In other words, it's pushing up harder than the weight is pulling down, and therefore you'll get this vertical net force that is in the upward direction. And in fact, that value, that difference between the normal force and the size of the weight force I'm just labeling as negative by subtraction here. If you actually figured out the net force, it's actually equal to your mass, not your weight, your mass times the upward acceleration, because net force, or the sum of forces, is always equal to mass times acceleration. All right, so here's a little extra question for you. What is the normal force if the elevator cable snaps? In other words, suddenly everything's falling down. It's in free fall. We're going to assume there's no air resistance as this elevator box just plummets down to the bottom of the building with you in it. Obviously, this is a horrible situation to be in. Most elevators have safeguards that prevent this from happening and actually lock the elevator in place or slow it down so that nobody gets hurt. But there have been accidents with older elevators. If this thing falls, you and the elevator will be in free fall, falling down. And in that case, you'll have this elevator that's moving down, and let's just say the whole elevator has a mass of m. The weight force down is still equal to m times g. It does not change just because you're falling. Your apparent weight changes. Your actual weight does not change. But now, because you're inside the elevator and both of you are accelerating downward with an acceleration of g, you're both accelerating at the same rate of acceleration, there is no normal force anymore. The floor is not providing any support to you, and in fact, the normal force is zero in that case. So in this particular case, the normal force is zero. That is, your apparent weight is zero. That is, you feel weightless while that's happening. And in fact, in the space station, in the International Space Station, this is what's happening all the time, for months at a time, for astronauts that are up there for long periods. They are continually feeling like they're falling. They just get used to it. Only people that can deal with falling for 6 months in a space station can handle that on their stomach. But that's what you feel like. You literally feel like you're in free fall for months at a time in the space station. All right. Number 29, in deep space. So when I say deep space, I mean you're not near another planet or a star or a moon, something with gravity. You're away from everything that has significant gravity. And it says you have two objects. You have a bowling ball. Bowling ball there. Sorry, a bowling ball. And you have a little ping pong ball. All right. And there is going to be, because they each have masses, we'll say that's the mass of a ping pong ball. And this will be the mass of the bowling ball. All right. The mass of the bowling ball is obviously much, much greater than the mass of the ping pong ball. But the question is, if these two are attracted by gravity towards each other, and the reason they're attracted is because they both have mass, it's not going to be much gravity. It's going to be a really, really, really tiny amount of gravity. And we haven't gotten to the formulas for how to determine that. That's later in this lesson. But I'm going to tell you, any two objects with mass have gravity, a gravitational force between them, no matter how big or how small. Obviously, the bigger the object, the greater the gravity. And objects this small, it is incredibly hard to measure gravity, a gravitational force that's this tiny. But there is something in theory. There is a gravitational force. So the question is, and I'm going to actually separate these a little bit further here. Let's say the ping pong ball is out here. They're going to be drawn towards each other. And the question is, how do the magnitudes of these attractive forces compare? Because the ping pong ball is attracting the bowling ball, and the bowling ball is attracting the ping pong ball. Which force is greater? Now, we haven't learned the formulas, but we have learned Newton's laws of motion. And Newton's third law says the force that one object has on a second object is exactly equal to the force the second object has on the first object, just in opposite directions. So these forces are equal. So the force of the ping pong ball on the bowling ball is exactly the same as the force on the bowling ball, of the force of the bowling ball on the ping pong ball. They're just in opposite directions, but they're equal forces. And this is exactly the same situation that I mentioned earlier, where a person standing on the Earth has a gravitational force pulling them down, but at the same time, they are pulling on the Earth with exactly the same gravitational force upward, pulling the Earth upward. Now, you would, if you were to fall, you would accelerate with G as your acceleration. And you might say, well, the Earth isn't accelerating up. Well, actually it is, except the acceleration up is so incredibly tiny because the Earth's mass is so much bigger than yours. So more mass means less acceleration. But in theory, the Earth is actually accelerating up into you, but the amount is so incredibly tiny we could never hope to measure it. All right, number 30. In deep space, gravitational forces exerted on the bowling ball and the ping pong ball are equal, okay, and opposite. We already know that. How do the accelerations compare? Now, we've already determined that the forces are absolutely identical because of Newton's third law. But does that mean the accelerations are identical? No. And here's the reason. Yes, the forces are identical. So I'll just write that the force of the bowling ball on the ping pong ball is the same as the force of the ping pong ball on the bowling ball. All right. Yes, those forces are equal. If you want to be completely perfect about this, we can include a negative sign because one's in opposite direction of another, but we're just talking about how big the forces are. Yes, the forces are identical, but remember, this is on the ping pong ball, so that's equal to the mass of the ping pong ball times the ping pong ball's acceleration, and this one is equal to the mass of the bowling ball, because it's on the forces on the bowling ball, times the acceleration of the bowling ball. And these are all equal. They're all equal to each other. And therefore, this is equal to this. And you'll notice these are very different masses. If this mass is much bigger than the ping pong ball's mass, then the acceleration of the ping pong ball will be much higher because the mass is much lower. They have to balance each other out, whereas the mass of the bowling ball is higher, so its acceleration will be lower. You might say, well, how am I going to remember that? Well, remember it this way. Let's say instead of the forces being on each other from gravity, you're just kicking a bowling ball and you're kicking a ping pong ball with exactly the same force. The forces are identical. One has much bigger mass than the other. If you kick the ping pong ball with a certain amount of force, that ping pong ball will accelerate to a great degree. It'll have a very high acceleration. Low mass gets a high acceleration. Whereas you kick the bowling ball, besides breaking your toes, it's going to have a very low acceleration because the mass is so high. So this is an interesting situation where you're taking Newton's third law and then you're combining it with Newton's second law. Remember, the second law says a net force on an object is equal to the mass times its acceleration. And Newton's third law says two forces between two objects where the forces are on each other, those forces are identical. But just if they have different masses, they're going to have different accelerations. So the acceleration will definitely not be the same. They'll be opposite directions and much bigger for the ping pong ball. All right, so this is a combination of using Newton's third law, and this is Newton's second law right there. All right, that tells you how big the acceleration is. All right, so it's a combination of the two laws. Question says, where will the balls meet if they're released from the position? All right, so you remember you have the big bowling ball and you have the little tiny ping pong ball. They're both being drawn by the same gravitational force, but the acceleration of the ping pong ball is much greater. And as a result, when they finally meet, they're going to meet pretty close to a point that's much closer to the bowling ball than it is to the ping pong ball, because the ping pong ball can accelerate much faster than the bowling ball, so it'll travel much further before the two come to a meet. So the balls will meet very close to the bowling ball, maybe even right here, very close. All right. Question 31, and this is the last question of the mandatory questions. The last two questions, questions 32 and 33, are optional, more advanced questions. All right. 31 says, a small car collides with a large truck, which experiences a greater impact force. Well, if we have a big truck and we have a little car and they collide into each other, if we call the big truck A and we call the little car B, the force of A on B is exactly equal to the force of B on A. That is Newton's third law. I'm going to say it over and over again. They're just in the opposite direction, so we'll just put a little negative sign there. They are going to be the same. Will they do the same damage to each other? No, because one has much more mass, so it will accelerate much less. In fact, in everyday English, we would say it will decelerate much less. It'll change its speed much less than the little car will. And you can imagine that if you had a big truck hitting a mosquito, it's the same situation. They have the same force on each other, except that same force on a mosquito with a very tiny mass will result in an enormous acceleration, crushing the mosquito, whereas it'll have no effect on the big truck. Well, you get a similar situation with a big truck and a little car. So, and that's because Newton's law tells us the forces are equal, but it doesn't tell us the accelerations are equal. All right, that is because the masses can be different. So no matter how fast or slow they hit each other, no matter how massive one object is relative to the other, they are always going to collide with the same force on each other, period. That is Newton's third law. All right, and you can stop here if you want. We're going to do two more that are advanced. You're not required to know these. Number 32, you observe a force, F, that is not exactly horizontal or vertical. In other words, it's at an angle. So if I just draw that, it's at some angle, and we'll say that angle is this angle here. We'll call that theta. And here's the force. It's not exactly vertical. It's not exactly horizontal. If you want to find the x and y components of this, what do? Well, here would be the y component of that force, and here would be the x component of that force. If you were to add this vector and this vector together, you would get the original force vector. And how do you do that? Well, you have to know a little trigonometry, and the answer I will just tell you is you use the sine function to calculate x, you use the cosine function to calculate y. So it's the original force, the amount of the original force, the magnitude of the force, that is how many newtons it is, times the cosine of this angle will give you this force, and times the sine of that angle will give you that component force. And finally, question 33. In the picture to the right, in which case 1 or 2, is the normal force on the sled greater? All right, well, how would you figure this out? All right, so the normal force is the force that's going to be up from the ground as your weight force is pushing down. And if weight and normal force were the only forces involved in the vertical direction and you were on a flat ground, those two forces would be equal. In other words, if we had a sled on the ground, here's the weight force, the normal force would just be pointing straight up, and it would be the same size as the weight force if those were the only two vertical forces. But you don't have that situation here. You have an additional force besides the weight force and the normal force. You have another force. In case 1, you have a force pointing downward at an angle, and in Case 2, you have a force pointing upward at an angle. All right. Well, in case 2, your upward force has two component forces, and one of them, the vertical component, is pointing up, whereas in case 1, the vertical component is pointing down. So we're only interested in how these pushes or pulls are adding to the vertical forces. In case 1, you're pushing down even harder. So the weight is pushing down with a certain amount of force, and then you're pushing down on top of that, or whoever's pushing the sled is pushing down and forward, but there's a certain amount of down force added to the weight force, and therefore the normal force has to be higher in this case, because it has to match two downward forces, the weight force and the pushing down component. Whereas in this case, the person pulling the sled is actually partially lifting the sled, lifting up from the weight force, and there you only need a little bit of normal force to match the weight force, because there's a certain amount of upward force helping it along. These two can work together to match the downward weight force. And that's what's described here. And that concludes this part of the lesson.